So that brings us to the Langbein Award, which is in form of a lecture. How many of you plan to be in the luncheon meeting? Just out of curiosity. I hope several of you, because there we'll present many more awards to our graduate students, and also we have 2 union awardees from the hydrology section, which I don't know if they are here. Gunder? Yeah, Horton Mental. So we'll mention that in the luncheon, but congratulations, Gunder. And is Wilf? Stand up. And Wilf Bruchard? Is Wilf here? He's the Bowie Medal. Oh, Wilf, congratulations. So the Walter Langbein lecture is a big honor for a senior member of the hydrology section. Tisa Ilangasikar is the 2015 awardee, and it is my real pleasure to introduce Tisa. The citation reads, "For defining the field of intermediate scale experimental methods." The introductory remarks will be given by Mary Hill.
Hi, it's my extreme pleasure to present Tisa Ilangasakari as the 2015 Langbein Lecturer. Tisa's talks are thoughtful, inspirational, and very dynamic. They communicate expertise, vision, and contagious enthusiasm. We're in for a treat. Tisa's PhD focused on groundwater modeling with Hubert Morel-Seytou at CSU. He proceeded to become the most prominent experimentalist in intermediate-scale sandbox-style porous media flow and transport, including study of NAPLs. Indeed, Professor Ilangasakari has largely defined that field. In the late 90s, I was fortunate enough to work with Tisa on a highly complex subsurface characterization experiment in a 10-meter-long tank that was 1.2 meters high. Somehow, Tisa got graduate student Gil Barth, with whom I co-advised, to fill the tank with 2.5 by 25 centimeter lenses of 5 kinds of sand, an incredible effort. I was excited because the tank was long enough that differences between the in situ and lab measured hydraulic conductivity values could not be masked by boundary condition errors as had occurred in most experiments. I like to think that it remains the most rigorous study of hydraulic conductivity measurements that has been conducted. I'm sure Tisa will talk about some of those fun experiments. Of special note in AGU was 5 years as editor of Water Resources Research. Other efforts included being team leader on the National Science Foundation reconnaissance team to Sri Lanka in 2005 after the devastating Indian Ocean tsunami, and his current position as president-elect of the International Porous Media Society, which brings together scientists from academia, research institutions, and industry. And now I'm happy to present Professor Tisa Ilangasakari, the 2005 Walter Langbein Lecturer, for his lifetime contribution in subsurface science and engineering through innovative experiments that will lead to better understanding and models needed to solve our challenging problems in hydrology and the environment now and into the future. Thank you. Tisa.
close this and go to yours. Don't forget the award ceremony and, of course, the lunch, which is just following. And we have to close this. We have to close that and go to yours.
Okay, thank you very much. Actually, I had to negotiate the time with FE, so I actually had to read this response to the citation because I didn't want to miss anything. But I think I also requested a portable microphone because I'm not used to giving this type of lectures under a lot of lights. But I'll try my best. So before I do that, I'm going to thank you, Mary, for the kind words and nominating me to receive this great honor. I also would like to thank Peter and Majid for this support. This support means a lot to me, as the nomination not only came from 3 highly respected hydrologists who have made lasting impacts on the field, but who have also impacted on my work as collaborators, and more importantly, who I can proudly call friends. I'd like to thank the award selection committee too for giving me this opportunity to present and share my experience at this largest gathering of world's hydrologists, many friends and some family in the back. It's a great honor to be selected for this lecture, as it's named after Walter Langbein, and also among the distinguished hydrologists who have given this lecture in the past. Starting with Peter Eagleson in 1993, many of the past lecturers I have admired and learned from. Some have influenced my work in many ways. Few have been collaborators, and some I consider to be my mentors and friends. I had the pleasure to know and collaborate with Mark Meyer, who was a 1998 lecturer. I did some interesting work with him in the Greenlands, and the first Sri Lankan to go to work in the Greenland, I suppose. I also would like to congratulate Professor Gutsat, who was the 1997 Langbein lecturer, for his Bowie Medal and continually inspiring us with his seminal contributions. I'm glad he's here in the back. After listening to my talk, I'm hoping it will become clear that the type of research I worked on the past 30 years could not have been done alone. It required teamwork by a large number of students and postdocs with whom I was fortunate to work with. Also, there are many others who helped to facilitate my research, including collaborators, mentors, and most importantly, a very patient family. I'll try to recognize many of them during and at the end of my talk. I want to use this opportunity to let you know how fortunate I am to be standing here, considering where I started. I was raised in a small village in the tea and rice growing central hills of Sri Lanka. Not a bad place for a hydrologist, with 150 rainy days and 80 to 140 inches of rainfall, annual rainfall. You learn a lot of practical concepts about fluid mechanics, hydrology, hydraulics, dams, soil, and mud, just playing in mountain streams and muddy rice fields. I was also fortunate to have parents who instilled in me the value of hard work, education, perseverance, and provide opportunity to support to get the best educational available in Sri Lanka. I'm also humbled by the fact that there are many in this audience who deserve this honor as well, and I'm thankful to all of you for taking the time to come and listen to me, even though my lecture competes with a person who makes a very expensive car, among other things, and he has cars to sell, but I think I don't have much to sell, so I'm happy that you're here. I accept this on behalf of my students and my collaborators. Thank you all again for this great honor. So that. Okay, so now I had to figure this out. So actually, so I'm going to talk about some experimental work I have been, experiment technique I have been using for the last almost 30-some years. And as you know, as hydrologists, we have achieved a lot in the last several decades, and all the research we have doing in trying to understand the fundamental processes has helped up to improve our models. I think there are new technologies coming from sensor technologies and measuring methods which is going to impact our field tremendously. And I'm hoping that the same technology development help the type of research I do with experimentation. So today, I'm going to be focusing on experiments only. Even though I'm going to talk a lot about experiments, my research has a very strong modeling component, also done in multiple scales. But I'll just focus on the experiments today, mainly because of the time limitations and to give a little more focus to what I'm trying to present. So Walter Langbein has done, Dr. Langbein, through his scientific contribution, has served our field quite well. And there's a article by James Judge, who was also a Langbein lecturer. I don't remember, maybe second lecturer in Langbein. And actually, so he, this article actually gives a lot of details about a lot of the work he has done. And more than that, I think he was the starting editor of water resources research. This is the first edition I have in my collection. And I was also very fortunate to serve as an associate editor for many, many years, and his editor not too long ago. And if you look at his work, you'll see that Walter Langbein started his work as looking at problem of groundwater, control of groundwater. So if you look at the papers which are published in the first issue, there were like 5 papers in groundwater, and these are close to 50% of the papers. But if you look at a recent publication, this one I just looked at the October issue, you'll see that the field has diversified quite a lot. And I think as subsurface people, we work a lot on carbon dioxide, carbon sequestration, trapping, non-fecal transport, hence jump, natural gas production, so you can treat those things. So when I was actually the editor, I remember I used to handle about 500 groundwater-related papers. So I'm sure there are in the audience a lot of my people you had to deal with. Some probably very happy people, some maybe not very happy because I rejected some papers, but I still consider we friends. So I think what this says is that the groundwater is an area where there is a growing area, and then we have a lot of opportunities for young hydrologists to work in and impact the field and make a contribution to the society. So I think it's a good place to start is to recognize that all problems are global. So we are living in a very interconnected world, and if you look at this data from UNESCO, you'll see that in 2023, the available global population will decrease, the available water will decrease by 30%. And in 2000, the number of people that died because of water quality exceeds 2.2 million. So you can see that the work we do as hydrologists is quite important. I think we'll see actually in my presentation, I'm going to talk about some of the problems I was fortunate to be involved in this type of work which are more impactful. So when I was in the plane this weekend, I sort of found that there's an article about the issue of groundwater, and also I have a certain other motive here because this lecture is going to be archived. So when I say something here in 10 years, if I say something wrong, then you can always look back and say, I think what it said didn't happen. I think these are 2 of our friends, hydrologists, and they are making these statements. It's interesting to see what they are saying is really come true in another 10 or 15 years. I think this is a very, very serious problem we are dealing with the issue of groundwater. So the primary driver for water problems, I don't know how to say this, but has to do with population increase. So the global problems are all driven by increase of population. And they are forcing us to share the diminishing natural resources that include water. As you see, it is expected that the world population is going to be going 1 billion people every 13 to 14 years from 7 to 1.3 billion now. So the alarming thing is that humans already use 54% of the available fresh water. So I think we have some serious problems in front of us. So I try to I try to categorize some of the problems under these 6 categories. First, we are looking at the potable water. So as hydrologists, we are going to be responsible, or we have to do research to address the issue of sustainability and the quality of water. And the second one is the global warming. There are a lot of hydrology and water dimension to global warming. As you know, 2014 was one of the worst years, and it's going to be worse this year, looking at the temperature rises. And then the third problem is that we had to deal with the poor, the health issue related to water quality and the climate, and the food security, which has to do with irrigation and groundwater mining. And the water energy nexus, we hear a lot about hydraulic fracturing, and this it has a very strong water dimension to this, and natural disasters, floods, droughts, and tsunamis. And I think everything we do is useful in all these problems. This is not an exhaustive list, but there are many problems related to the water. So the primary thesis of my presentation is how carefully designed and theory-driven experiments at various test scales can play a central role in providing answers to critical scientific questions, and how they will help to fill knowledge gaps to address emerging problems in hydrology and water. I'm just reading it, but I want to emphasize something important here, that the experiments has to be theory-driven. So if you are designing an experiment, if you are going to make any sense out of your experimental data, then you have to have a theoretical foundation. Actually, when I got the Darcy medal from AGU, I did a lot of reading about Darcy, and Darcy didn't run the 1832 experiment just because he was trying to discover Darcy's law, but he had a good understanding of fluid mechanics. So he ran the experiment. Before that, he understood Stokes' equation, and he was demonstrating how it works. So in my lecture, you will see that to become a good experimentalist, you need to have a theoretical foundation. Also, to become a good experimentalist, you need to have a lot of patience. And then I think it takes a lot of time to do the type of stuff my students and me and some others, of course, here have been able to do. So my outline of my talk is going to be, first time I'm going to actually introduce, as you know, I'm from Sri Lanka, introduce an ancient irrigation water storage and distribution system in Sri Lanka, where physical models and observational methods may have been used in design of these systems and their operation. And I'm going to also take this example later. I'm going to talk about this again, how things can go wrong when you try to system which were designed thousands of years ago. So I'm going to make is my presentation. Then I'm going to introduce a class of problems. It's a good time to get hydrated. Then I'm going to introduce a class of problems at the physical interfaces in subsurface systems. And then I'm going to introduce a multi-scale testing and a unique test facility we were able to build in the last several years. I'm going to take 3 examples from our past and ongoing research to demonstrate the challenges, impacts, and opportunities these experimental methods provide. And finally, I'm going to wrap up with some thoughts on subsurface research directions. So, as you know, Sri Lanka is a tropical country, and then early inhabitants who came to Sri Lanka actually settled in the northwestern, this part of the country, where the average rainfall is much, much lower than the whole island. I don't remember, it's very low compared to the 140 inches I get somewhere here. So when they came here, because this is a rice growing area, to sustain 2 seasons of rice growing, rice takes a lot of water. So they actually built this very sophisticated irrigation system, which was started in 300 BC. Actually, these things have very large dams, very long earthen dams, and they have a very sophisticated system. All these dams built almost 300 year BC consistently had this very highly designed control system, and they sort of demonstrated they understood some principles in hydraulics, and these dimensions are not arbitrary. And then so this is actually turned out to be, I was a little biased here. I selected one of the oldest dam, which is named after me actually. It's called Tissa Vava. Tissa Vava is the Tissa Dam. Like, the Tissa is a very common name in Sri Lanka. All the kings, and there are a lot of good guys. There are bad guys named Tissa too, but there are a lot of kings named Tissa. So this particular dam has a 54-mile long canal. This is one of these canals they built. And this, interestingly, it is 40 feet wide and is 17 miles the first 70 miles had a slope of 6 inches per mile consistently. So you always wonder how did you do that long ago. And today around 12,000 ancient small dams, 320 ancient or large dams, together with thousands of man-made lakes in lowlands, these are still in operation. Now I'm going to come to this problem again because these things during the due to various reasons, foreign invasion, the people in Sri Lanka from that area, they first settled, moved to the hill part of the country, and the things due to malaria took over, and they were completely abandoned. And then the British discovered this system, and they diverted the water from the wet zone, some places get 180 inches of rain, through a mountain system into this, and they fed this system. These are thousands of these lakes and reservoirs. And then I'm going to actually bring you back at the end of my talk, one of the problems with using this ancient system, again, after 3,000 years, without understanding the socio-economic and political condition existed at that time. And this has created a very serious problem in Sri Lanka, which is a kidney problem. I'm going to talk about that at the end of my talk. So you always wondered how were they managed to do that without the benefits of the mathematical and calculus and computers we have these days. So I have been actually thinking about this for a long time. When I go to Sri Lanka, I talk to scientists in Sri Lanka, and then they have different theories, but I think one of the things sort of convincing was that they use some sort of pilot canal going in parallel to these canals. So the question you always ask is that if you have a pilot canal, how do you transfer that information from the model of the canal to the main canal? They also had a system of almost like a pan evaporometers. They are basically made out of clay. So they were acting like a model of the dam. So they look at the people who operate these dams, they look at this clay pot, and they were able to extrapolate that information to the lake. That's how they were running. So this is sort of related to what I'm going to talk about today, because I'm also going to make the argument there are a lot of things we can do by observing. They went through a lot of trial and error like we do in our labs. So this is still true the way we do things now. So I'm going to, again, get into more technical part of my talk, is that I'm making the argument that most of the exciting problems are the interfaces. So there are a number of interfaces listed here. The first one is the interface which is very, all of us know about, the unsaturated zone, which is the water-air interface. And the second one is the water non-aqueous liquid interface. I'm going to use the word NAPL after this. NAPLs are liquids which doesn't dissolve very fast, and they stay there in the ground for a long time and creates all sorts of contamination problems. The other interface is the river aquifer interface, which I did for my PhD work many years ago, where this has to do with the water infiltration, and then and of course I forgot the water table. This is another interesting interface which is very important in a lot of hydrology and water quality problems. And then the snow atmospheric interface, which has to do with glacier melt and snow melt. And the land atmospheric interface, this is one of the most difficult one I'm going to talk about also at the end. And the land ocean interface, which I'll also talk about. So I'm going to actually focus on these three interfaces in my talk today and try to show how experimental methods are used in land atmospheric interface. Those who wonder how I'm going to use a tank to study these two problems. So what are the challenges of interfaces? First one, the topology is hard to define. If you go to a porous medium at the pore scale, you immediately see that you cannot really go and see these interfaces. It's almost impossible to define these things. And some of you are working on this problem know that this way the interface behave, they evolve, is related to the constitutive models we use in this type of modeling. And then we look at the land atmospheric interface. This is also very hard to define at the different scales. And then the second one is that if you go to this interface, you see there's a separate phase and abrupt transition. You move from one fluid, completely different properties, to another fluid across the interface. And then the simultaneous flow of energy and mass flux. So you see the land atmosphere interface, this one, in this case, when the mass dissolves from the non-aqueous liquid into the water, then it creates the plume, and that produces the contamination downstream. And also these are very difficult problem to model, because you are looking at, in this particular case, for example, you're looking at the Navier-Stokes equation here and Darcy flow here. How do you deal with this interface, this transition zone? So I'm going to use my some of the work I did for my PhDs. I won't mention the year, that will give you a hint, you know. so this one actually related to the interface problem I mentioned earlier. Also, it sort of has some relationship to Walter Langbein work, some work he did. So what I did was that I did use a linear systems method to model a stream of a system, and then divide the stream into these linear reservoirs, which allows the water go from here to here, and also we linearize the groundwater equation. So this allows you to develop a linear systems model, which can be used in optimization models, etc. So you can, and people who do this type of work know the advantage of linearizing these equations. So I applied this model. This model was actually used in developing a South Platte River aquifer simulator. And when I'm looking at Langbein's work, Langbein actually published a paper in 1940 where he actually commented on the application of this so-called Muskingum method to a reach in North Platte River. This is the South Platte River. And he came to a conclusion that this reach is too long to be modeled by one parameter, and he suggested that we should divide it into two. Actually, I actually was able to use that concept in my work, that because in South Platte River, actually if you read James Michener's book about Centennial, they say the South Platte River is a sorry example of a river. Because recently the river goes dry in few miles, the water comes back, there are return flow. So it's very difficult to model this. So I was able to actually calibrate the model better by dividing the thing into small sections, then that will give more degrees of freedom. So the point again is that, so these people like Langbein thought about these problems many, many years ago before we were born. So now I'm getting back to the technique I'm trying to promote here. Maybe brainwash some of you. So the whole idea here is that we are looking at the pore scale here. The pore scale is actually three-dimensional. And then the field scale is also three-dimensional. As modelers and experimentalists, we try to move from here to here. So this is sort of the grand challenge of hydrology in some ways, how to upscale. So in the process of moving from here, we use one-dimensional test, two-dimensional test, three-dimensional test system models. The reason for doing that is we want to reduce the complexity, sometimes the complexity of the experiments, and the cost. So if you look at when you move from these one-dimensional, simple, homogeneous columns to the complex field, the complexity is a result of two factors. The dimensionality, most of the time when you characterize the flow in a one-dimensional systems, you are using homogeneous sand and this one-dimensional flow, but then when you try to upscale this problem from one dimension to three dimension, that introduces the complexity. Second one is the heterogeneity, because when the world is very heterogeneous, so when you look at these upscaling methods, you have to deal with this problem. So what we have done in our work is that, so what we have done is we define a field scale called intermediate scale. The word comes from what is intermediary between the column and the field scales. And then in the laboratory, so this scale is where the field scale processes can be mimicked under control conditions. The control is quite important because in the field, we cannot control things. Basically, all the models are partial differential equations some way, form or another, and if you don't the initial condition, boundary condition, then you have trouble capturing what's going in the field. So in this scale, we can go from a millimeter scale to 10-meter scale. Even though it's called intermediate scale, we don't run experiments at 10-meter scale all the time. So we can take measurements at any scale of interest from millimeters to 10 meters, and then look at the multiple scales, how these systems behave. So I'm actually taking some example here, starting from a simple 1D, 2D, 3D, and going to the field system. So we have done this type of work where we can move from different scale to scale. So these are some of the testing systems used, and then we use 3D tanks, 2D tanks. We use a lot of sensors, automation. We grab samples. We fill tanks with very complex heterogeneities, about 30,000, 35,000, 28,000 cells in this case. And then this is so what can we achieve in this scale? We can control the initial and boundary condition well. I mentioned this area. And then you can actually, heterogeneity is always a problem in the field because we can never get exactly what is going on in the field. So we control the heterogeneity in the laboratory and we design the heterogeneity. And then the precise data and fundamental insights can be obtained using this scale. So I'm going to take 3 examples to challenges, impacts, and opportunities. The first one is I'm going to take an example how to move from pore to the field scale as applied to remediation and carbon sequestration. Second one, I'm going to look at the societal and humanitarian impacts on some work I did on the tsunami damage in Sri Lanka and South Asia. And third one is opportunities. So this is actually past work, and these are some of the areas we are trying to get into now and show what other opportunities exist using these techniques. So in these examples, I'm going to use this example to show how good science questions can be raised. So when you are doing research, you need to raise the good question, either explaining a phenomena or make observation and based on some data and some identifying knowledge gaps. All these examples, you will see some of these features. And then you need to develop a theoretical foundation to drive experiments. Like I mentioned, without a good theory, you are going to fail in your experiment. And the next one is how to design this experiment. These are very complicated experiment to design. I'll show in a minute later. And then how do you represent these large-scale processes in the lab, and then how you bring the complexities from the field to the lab. And then how observation and experiment data are used to interpret new insight and improve conceptualization. I'm going to also make the argument that the experiments like we are doing will help you to better conceptualize these systems. Then how this new improved knowledge is used to improve models for prediction. Looks like I have more time than I thought. Okay, so I was debating about this until last minute, and I actually decided to put all the people I have worked with me, and I have many, many students. I put this thing here, especially which is going to be archived, and someday people look at it and say, you missed my name. I'd be very careful not to make sure their names are spelled correct. So they do it all the time to me. So you see all my students, then I have some all kinds of collaborators. You see some of them are sitting here, and then I also want to acknowledge for funding, and I think I got quite a bit of money from all these agencies. I saw Tom in the audience earlier. NSF has been a very strong long-term supporter of my research. So I'm going to introduce this. So even though I have been doing research on non-aqueous liquids, when the CO2 business came around, the sequestration, then I found a lot of research I did on carbon sequestration is applicable to this problem. So this is actually an IPCC report. Basically identify 4 mechanisms for trapping. How do you get the CO2 into the subsurface and allow it to stay for a long time? So they happen in different time periods, 20 to 40 year period for structural trapping, and then and to thousands of years in mineral trapping. So I'm taking this Sleipner carbon capture and storage project, which I've been going for a long time. So you see these are images of geophysical data collected at this site. You could see this layering and heterogeneities I'm going to be talking about. So what happens is that when the CO2, which is the supercritical CO2, which is a lighter than water fluid, lighter than the brine fluid, it started moving on due to buoyancy and hits a cap rock, and there's on the top of the formation, there's a cap rock, it started accumulating the cap rock. And while it is moving, it also, it's trapped residually. It's trapped in the soil pores, and it creates this residual trapping. And then also another phenomenon which is not discussed is this trapping which has to do with, you see this layering produce what we call macro scale trapping, which has to do with the texture transition between these different layers. And then the third one is the solubility trapping. These are all from my experiments which I'm not going to present today, but these are some of the experiments due on soluble trapping. And finally, the mineral trapping is a very, very long-term trapping problem. So what happens is that, next slide. So to understand this capillary trapping effect, so what I'm showing here is that this is a formation with a very coarser soil and a finer soil. When the non-aqueous phase liquid, which is a non-wetting fluid, comes to the interface, and for this fluid to enter this here, then it has to overcome entry pressure. So once you overcome the entry pressure, then it breaks through. So this is an example where the entry pressure hasn't been overcome, it started pooling. So that's why it creates this trapping effect. But this is actually a really good thing in carbon sequestration, because carbon sequestration, the whole idea is to keep the stuff underground to stay for a long time. And remediation is not a good idea, because if you stay trapped, then it creates a long-term source of contamination. So to do this, what we did was look at the carbon sequestration problem. We recently finished some experiments in a 8-foot long tank. So in this first case, we are showing in a homogeneous case. But the most difficult thing in this experiment is, as you know, CO2 doesn't stay like a liquid when you bring it to the ground surface. So we had to come out with an innovative way of running these experiments under ambient condition in the laboratory. So what we did was we used these surrogate fluids, and we changed the composition of the fluid in a way that the dimensionless numbers, for viscosity ratios, surface tension, all that stayed the same, at least very close to what the field system. So we can actually do a lot of the experiment in the laboratory condition and extrapolate this information to the field. So then we fill the tank with a correlated random field. You could see that the trapping mechanism I mentioned earlier now increased the trapping in this problem. You see that the trapping is much higher because this barrier effect I mentioned earlier. So we have a system where we can quantify this trapping. We have an X-ray system where we shoot X-rays through the tank. And then, actually this picture is slightly shifted, but you could see that we can get very accurate data on how much of this stuff is trapped here. And I like you to notice that the volume, these are different scales, but the volume in both these cases are the same. And you see that the high saturations are at the top of the formation here. So this is the good thing in carbon sequestration. So now I'm going to go to show how do you take a theory from a very fundamental theory and bring this theory into a porous medium to represent elementary volume scale and go to the intermediate scale and go to the field. So the example I'm taking is coming from chemical engineering, where we are looking at dissolution of a plate. So chemical engineers has very nice experiments like this where we can look at this closed form solution. So basically what we do is we look at the momentum transfer in the boundary layer, and then you see the Reynolds number comes into this solution. And then we will also look at the mass transfer controlled by diffusion. So when you combine these two equations, you can develop a nice looking partial differential equation, and you can solve it. And you solve it, you get this relationship between the Sherwood number and the Reynolds number and the Schmidt number. And these numbers are defined here, and the mass transfer rate coefficient here is expressed in dimensionless form. So when you have this type of relationships, it allows you to develop models and move into different scales, like I'll be showing later. So when I was my sabbatical at Stanford, actually I was fortunate to meet some, of course I know Peter for a long time, and I met a very bright student, and I gave this equation, and she actually took this idea, and then she did a simulation in a sort of idealized porous medium using a multi-physics simulator, and just solve the Navier-Stokes equation and put an Apple source and look at the dissolution. And then they generated the data. Then you can see that the fitted function looks at the same functional form as the original equation. Only difference is that you see these coefficients are not going to be, that coefficient depends on the geometry of the system. So this sort of gives an insight to whether we could take the same equation and move it into a porous medium. So now in the porous medium, the REV, and this is again sort of hypothesized for the, so this REV, you see that the nipple is stuck here. This is not a very accurate picture, but the idea is that the water is flowing into this tube, and this is dissolving, and this is dissolving into the moving water and create the plume. So now again the chemical engineers, and if you are really interested in this type of problem, you should look at like a Bird's book in transport phenomena, which is a very useful book, and you find all these interesting solutions. And then so this problem involves the dissolution of a tube. There's a flow through the tube, and then it's very similar dissolution of the plate, and then you can get a closed form analytical solution for this one. But in this solution, they make the R constant. So but in our problem, when the water flows through the system, the idea is that we are modeling this thing for a long period where the non-aqueous liquid is going to dissolve out. So we need to allow for the changing saturation of the non-aqueous liquid. This is again true for carbon sequestration. So we came out this equation. Now this particular equation, these are all empirical fitted parameters which we get from your column scale experiment. So once you get that, all these alphas are depending on that particular system. So then then the next question is, how do I get this into a larger scale? So when you look at the, these are real pictures of a spill. You see that when the non-aqueous phase liquid spill, CO2 or a solvent, it creates these pools and residual zones. These are called ganglia. When the water goes through that, so we hypothesize that this whole thing happening inside this box, the effective behavior is a mixing process. So if you look at this curve, we look at the mass flux coming out of this box as a function of the second moment, that is how the napple is spread. If you take the same amount of fluid and smear it, then you are going to expose there are a lot of interfaces, then you're going to produce more mass. So using this idea, we basically developed this upscale model where on the left-hand side, you see the upscale Sherwood number. On the right-hand side, you still have that Sherwood number I'm going to measure for the REV scale. And then we introduce the geostatistics of the system. The hydraulic conductive, the K field, will tell you where the water is flowing. And then this one will give you the vertical, the vertical mixing process. And then this has to do with the grid size we use. And this one, the dimensional moments tell you what the second moment of this is. So we actually have published papers on this type of work in the past. So now the question is, how do you validate this? I'm going to take this example, this experiment, to demonstrate some of the difficulties in running this experiment. So this is one of our tanks. So you see this tank has, we can control the flow. There are all these sampling ports. We can put thousands of samples out. This experiment runs for months and many months. Take a long time to set it up. We control the flow. This is a 16-foot long tank. And then we have all sorts of sensors to measure. And we also have ports to inject fluids, inject tracers. And then what we do is we use 5 highly characterized, we have to use more than this, but in this case we are using these soils which has orders of magnitude difference in hydraulic conductivities, allows us to use geostatistical methods to create the heterogeneity. So what we do is, and in this particular case, we kept the log mean the same, but by changing the variance, I could go from a highly heterogeneous system to low heterogeneous system. So now what we do is we have the spill, and we have the spill, and we fill the spill here, now pass the water through, and we take the samples. For these ports, and then, like I said, this runs for many days and months sometimes. So now on this, so what we have done here is we plotted, so we develop a model, and I don't want to get into the details of how the model works. The idea here is that, let's say that we are going to take the REV scale model and just arbitrarily apply to the simulation. On the vertical axis, you see the model. On the horizontal axis, the observed mass. If they match, they should be in the 45-degree line. They are all over the place. Each of these represent different grid sizes we use in our simulation. So now we take our upscale model. As you see that they match well. And I think it's not an accident why this is matching well, because we spend a lot of time in trying to get this thing to work based on different theories we were looking at. Okay, now I'm going to get into the second problem, which I believe is for societal impacts. So this is actually these two pictures are here because they are those from Sri Lanka, and there are some articles we wrote appeared in here. So I took a team, like Mary mentioned, to Sri Lanka, and then you probably recognize some of the names here. I think Bill is here, and then I think Scott is here. So I took a team to Sri Lanka, and then so basically. So I'm going to talk about this problem in the next example, basically show how we can make societal impacts in the type of work we do. So this is, as you know, 2004 Sumatra earthquake, one of the most unprecedented natural disasters in the world. The biggest earthquake happened in 1960 in Chile, and this one is actually started at 9.1 when they upgraded to 9.3. So what I'm going to, that 32,000 people died, there are 230,000 people died, and 32,000 people died in Sri Lanka. That's a very big number for Sri Lanka with 20 million population and about 560,000 people. So I want to actually, I don't know how to do this. So I want to do this simulation. So I want you to watch this simulation from USGS, and this is important for the hydrologists to watch this, because when the wave started, when the earthquake happened, it took 2.5 hours for the wave to hit Sri Lanka. I want to see how the wave wraps around the island here. And then actually they don't name the country. The end of the video, they'll tell you where it is. Sri Lanka, India, as you know, the wave went around the world and it came back again too, you know. So this is a major wave. So now, actually, fortunately for us, actually, there was a satellite flying around at that time, and they had the sequence of pictures I'm going to show. So this is before the tsunami, and then this is during it was happening, then after tsunami. Actually, this is a picture. These pictures are taken somewhere around here, and if you remember, the wave went around here, and this is the normal way the beach looks like. And I want you to observe the ground here is all green and lawns and roads, etc. And now, so this is an interesting thing happened with tsunamis. So what happens is when the earthquakes happens, the water gets sucked towards the earthquake, and then the beach started expanding. So a lot of people actually went, after the tsunami, we went to the field, actually some of you went with me. So we saw a lot of destruction and then a lot of deaths, and we went to villages where many people died. And then you see people in the Sri Lankan history, written history of 2,500 years, nowhere it is mentioned for tsunami. So people are not ready for this. They saw the beach getting longer, kids were playing cricket and simple picnicking. It was a Sunday morning, and quite a number of people died because they were not expecting when the big wave came. The big wave came, as you see here, 30, sometimes 10 meters high wave, like a height of coconut trees. So it really devastated this area. So next slide I want you to observe is the one during the tsunami. See, when the tsunami hit, you see immediately, this is sort of not very clear, you see this water started ponding. And the water started moving through canals and rivers inland. And I'll show you some of the implications of that on the conceptual model we are going to be discussing in a minute. So now if you look at this picture, so this is the area which is affected by the tsunami wave. And then this is the coastal aquifer. These are the coastal aquifer. And a lot of the people depend on the water supply. A lot of poor people, the only source of supply are their wells in their backyards, the 50,000 which were damaged. They were completely damaged. Local ponding, the water started ponding here, and this contributed to persistence, and they completely collapsed. So these are very sandy aquifers. So actually, we knew about this, and people said that after 2 years, after tsunami, actually I was involved in a project where we were trying to clean wells and build toilets, etc. And we were getting reports after 2 years, the salinity hasn't gone away, and they had to still bring in water from other places. So we had some data from a site here. You see before the tsunami, the numbers, these are, you can read the units here. These are in microsiemens per centimeter conductivity. You see, this is a tsunami. Now this went up to 6,000 or 5,000, and after 2 years, it was this persistent. So the problem was that when we went to Sri Lanka, a lot of the people told us, oh, it's a rainy place, 2 monsoons, it's going to clean up, nothing's going to stay there. So, but it didn't happen. So we were sort of interested in why this was happening, and so we decided to run some experiments. So this is an experiment we did in a completely homogeneous idealized system where we simulated sort of tsunami event using the red dyed salt water. And you see that they started this convective mixing. The same thing happened in CO2, and it came down, and when the water started moving, it just basically completely disappeared. So this doesn't really contribute to persistence if you are looking at a completely homogeneous system. Now if we put a very simple layer of low permeability layer, the fingers came down. Fingers, as soon as it hit the formation here, it bypassed the critical Reynolds number, and the diffusion started dominating here. Suddenly the fingers, they started trapping in this formation here. Actually, this phenomena is quite important in remediation business, because a lot of sites we go, when the source is disappeared, it goes into these low permeability zones, and it rebounds, it comes back and contributes to persistence. So if in a situation like this, what happens is that if this water goes into a location where it gets stuck, then when the water flushes through, it's still going to this rebounding solutes will come back and contribute to persistence. So now we introduce a simple into the opening here. Now you see that the whole thing is going to be driven by advection. It's a gravity, but it's advection. It gets pushed through. So the thing people forgot in looking at the conceptual model was that the tsunami event is a head-driven event, whereas the rainfall is an infiltration event. So these are two different types of boundary conditions. When you are putting a very high head into a formation, it's going to push the water through places which are never going to come back. So this is the reason why the persistence was there, because the head-driven boundary conditions are different from the flux-driven boundary conditions of a tsunami. So this is the conceptual model. So conceptual model, traditional conceptual model, and some of us who are here saw this picture in Sri Lanka when they were giving presentation to us. So they said, oh, this is going to happen. This is a traditional saltwater intrusion model where the lens is here, the water came up, went here, and then it came down. When there's some contamination on the ground, it's going to get flushed out, everything going to be nice. And then what we found was that this was not, the data really didn't support this model. So we developed this new conceptual model, basically bringing these issues. Aquifer heterogeneity. I mentioned the aquifer heterogeneity earlier. Basically, it's how it contributes to the trapping and persistence of the persistence. And the bathymetry, this is quite important, because what we found out that one of my colleagues also from Sri Lanka, he took a team, they put a, BBC took a diving team, they went to locations where the worst damage happened. They found that the places where the coral reefs are there, the wave rate is reflected and nothing, the wave didn't travel into the land. So, and some places where this was not the coral reef was damaged, it just slid through the river system and went miles inland. And when it went to the inland, then it's when this micro topography and the stream aquifer interaction becomes important. The water goes into the river and it's going to slowly infiltrate. And there were people in the field told us they saw a tsunami wave coming from the land toward the ocean. The reason was that the river just pushed it and it just pulled it back. So then the head versus flux boundary conditions I mentioned earlier, this becomes important in this particular case. So now I'm going to talk about the last problem to opportunities, mostly looking at land atmosphere transition, the interface. And I have listed again a lot of the people here, funding agency. I want to identify 4 people here. So this is my colleague who was a wind tunnel expert. Actually, we started building this wind tunnel, I'll show in a minute, in the early 2000s. And then he was my supporter, and he was the guy who told me everything about wind tunnel. And my architect, Phil Greenberg, who actually came out with a very innovative idea of how to place the wind tunnel in a swimming pool. And then Kate Smith was here. Actually, she was responsible for designing the fairly complicated tank we had to use. And Paul Schultz and Andrew Trouts, who are the people who actually got the wind tunnel to come to life. And then Andrew is actually doing a postdoc with me now, working on some interesting problems. So these are some of the problems of the land data interfaces we have been working on, and I'm not going to spend time. So evaporation. So how do you understand evaporation processes? And chemical vapor intrusion. This is a very serious problem in contaminated site. And leakage of sequestered CO2 I talked about earlier. When you have a leakage, it's going to come to the ground and it's going to contaminate the soil surface, the shallow aquifer, and then leakage of sequestered CO2 coming out of the, I mentioned this earlier. Leakage of methane, this had to do with energy development, and we have done quite a bit of work on this one. And frozen soil, and when I introduce the wind tunnel, I'll show you we can freeze soil in the wind tunnel. And then we are looking at permafrost issues and construction issues. These are all climate change issues. And then carbon loading from plant growth and root extruders. And these are very important issues, because when the growing season changes, we are working on some ideas on this one now. Growing season changes is going to extrude a lot of extrudants, and then it's going to load CO2 carbon back to the atmosphere. Okay, so these are some of the work Andrew Trouts and he's doing for his PhD work, and so we are actually focusing on this zone, this shallow subsurface. There are a lot of things are happening. So this is a very complicated zone because there are a lot of soil disturbance and macroporosity. People are looking at macroporosity in the context of infiltration, but we are looking at macroporosity in the context of evaporation. We are looking at gas migration and the soil types and heterogeneity. I'm going to spend a little time talking about that in a minute. And then vegetation type and distribution. This is quite important because this is not only the vegetation, how the vegetation is distributed. We have some interesting data showing how the vegetation, when you have plant growing here, plant going here, how the soil actually adjusts itself so that plants will survive in these type of systems where they are competing for little amount of water. So we are finding, interestingly, the atmosphere plays a very important role in deciding how much this plant gets water, how much this gets water. There's a poster by Andrew on Friday. We could talk about this. Microtopography, and it's not only, they are not looking at flat surfaces. And then bare soil. Bare soil is like 24% on the land has bare soil evaporation issues. And a macrotopography, this wavy roughness. And soil moisture dynamics due to atmospheric feedback effects. They are looking at how the atmosphere itself affects these processes in the soil. So we have identified some knowledge gaps. Flow conditions that below the soil surface affected by atmospheric conditions, humidity, temperature, wind velocity, solar radiation, all this stuff listed here. And most conventional land surface models, these mechanisms are very crudely parameterized. And they are inconsistent even with the limited understanding of the processes which are happening at this scale. And also the scarcity of data. This type of data to validate these fundamental processes, you cannot get in the field for the reasons I mentioned earlier. Okay, so this is the wind tunnel I talked about earlier. So you see this is a 8-meter long wind tunnel. And then, so this is actually contained, I'll give you a little more details later. We have an environmental chamber, which is sitting, the wind tunnel is sitting in this one. So we started this about 2003-04, and we just completed about 2012. We are just doing some experiments now. And then, so the reason in this wind tunnel is important. This is not a conventional wind tunnel because for the reason that when you are looking at evaporation, if you are looking at soil, what evaporates from the soil, when the wind comes back, you don't want to have wet wind coming here. So we have to suck the air out and to dehumidify, put it back. When you are looking at gas migration, gas leakage problems, we don't want to bring the contaminated gas in, so we have to take the gas out, clean it up, and put it back. And then, so we actually control the wind speed, these ranges, and we can go sub-freezing, and then we also control the relative humidity. These are some of the things we can measure in the wind tunnel. And actually, so this is the swimming pool I mentioned earlier. So you see that the site was built in the swimming pool, and then, so we actually use a very innovative idea where we put the wind tunnel on the top of the deck here, and the tank was inside the pool. So these are some details. So we can actually pull the tank out and fill it, and then we can jack it up so that the soil, the bottom is just below the bottom of the wind tunnel, and then this is the soil tank is highly instrumented with soil moisture sensors, all sort of probes to measure very high data, because these experiments run for months. Actually, we are running an experiment now which have been going for like 3, 4, 5 weeks. So we are. So then it has, this is inside the wind tunnel, this is the box, so this is the soil surface. In this case, we have 10 centimeters now. Actually, we can move it about a meter width. And then we have all sorts of instruments. We have a LDV velocimetric system. We can measure very accurate velocity fields. We have a flame ionizing detector to detect gases. There's a lot of robotics to control, get the data all automated because they run for a long, long time. And then, so like I said, we ran many experiments, and I'm going to present some sample experiments. So one of the things when we are getting into the wind tunnel type of experiments to see how far can we use the existing knowledge about flow over a flat plate. So we were just investigating whether the porosity, when you have the soil, whether soil has an effect on the permeability soil has an effect. So what we did was we took a fairly coarse soil in our lab, the 5 soils, and then we filled the tank here, and in one experiment, we actually took the same sand and just create a sandpaper and look at and you see that this is not a complete graph. You see the velocity almost goes to 0 here. Now, when you look at this, we get the same velocity distribution. In other words, when you have a porous medium, the porosity really doesn't have any feedback effect on the wind velocity distribution. What is interesting when you go to the next one? So now we introduce the roughness. So we moved from the same sand and introduced gravel. You see immediately the roughness has effect on the boundary layer. So why this is important is that when you are looking at this coupled model, you need to capture these processes at a very, very small scale, and this make a big difference in the way things move through this interface. So this sort of suggested that how about if the surface roughness changes in this form. So this is make a very big difference, as you see here. If I take the velocity measurements here, or here, you see the velocities are quite different. And I'm not going to present this today, but I think we have shown that this type of variation on the surface condition create subsurface soil moisture gradients. Because when the soil is drying here, the capillarity will pull the water there. So you always assume that the atmosphere not doing anything, but atmosphere is actually working with the trees, trying to preserve water under the tree. So I mentioned this to Ignacio yesterday. So that's really exciting because the plant is really doing a lot of stuff to keep alive, basically. So now, so we look at the gas flux condition. So these are some equations. One of the equations is you can actually express the gas as a very simple equation, the atmospheric concentrations and the concentration at the surface, and then on the denominator you have the resistivity terms, this atmospheric resistance, the soil resistance. So it's important to note that when these things happen, both these resistance contributes to the gas flux. So if you look at the atmospheric resistance, you see that the atmospheric resistance depends on many things, and one of the things you can immediately see the wind velocity has a major effect on the resistance term. So if the wind velocity changes, then you are going to change the gas flux. So it's quite obvious. Actually, I forgot to mention this. So when you do experiment, one thing you discover is once you are done with the experiment, you get the data, it looks very simple. It's obvious. If you have done a really, really good experiment, if you realize that what you are seeing is obvious. So these things are obvious, but it's nice to get the data to show that the obvious is still scientifically true. So then we look at the soil roughness, you immediately see the soil sharpness has an effect on the dry and the partial saturation. So if the dry soil versus wet soil has an effect on the soil roughness. It's sort of obvious, but I forgot to mention this earlier. In the previous case, when the soil is wet or dry, it doesn't make any difference. So now the question is, so we have generated all this knowledge. How can I move this knowledge from this to this one? These complex things. So some of you are sitting here, working in here, say, oh, this stuff happening here is sort of useless here, maybe. So actually, it may not be useless, I don't know, but the thing is it all depends on all the parameters which are sensitive at different scales. So we are asking the question, we don't know the answers. I think invariably, when you go to the large system, you have to decouple these systems. You are not going to model the Darcy-Stokes models happening at the smaller scale. So the question we are going to ask is how large length scales we can carry this coupling so we don't lose the accuracy, but then when do we decouple these things? When you decouple, then we can model these things better. Okay? So that's the question we are asking in our research. So this brings us to the interesting work. We are just starting with Rainer Halbeck, who is sitting here, on this whole scaling issue. I think these people must have thought about this, but I think it's interesting to revisit this. When you are looking at scaling problem, we had a little time scale and space scale. The interesting thing is when you look at subsurface flow, when you look at scaling, there are different scales which have happened at different length scales. And the vertical scaling is quite different from horizontal scaling. This shallow subsurface, we are looking at all this action is happening, is pretty small compared to the large lengths we are looking at in the larger scale. So if you look at the post scale, the scale increases from this soil type to soil heterogeneity. So you develop a model looking at the heterogeneity, then you look at the vegetation distribution, that scale is going to be quite different. When you go to this wavy roughness, that scale is different. And then when you look at this one, you will see that the spatial scales going from here to here, suddenly you have to deal with the atmospheric boundary layer. Similar time scales, when you go to a smaller size scale, the boundary layer turbulence controls, as you go up, it becomes a diffusion problem. So these are some of the issues we are bringing into some of the modeling strategies and we are going to be looking at. Okay, this sort of brings to my end of my technical presentation. I'm doing okay? Yeah. she's happy. Okay, so now I can give my philosophize a little bit. So I have actually done, even though I was recognized for my work here, actually I started as a modeler. I spent a lot of models. This is a model we developed at the Rocky Flat nuclear plant for closure. It's a very complicated system where all sorts of nuclear stuff is going on. So we developed a very complicated model. And then also I had done quite a bit of field work. I had done work in Nepal, Sri Lanka, Philippines, and then also I do this type of thing. So my argument I'm making is that we cannot stay in these boxes anymore. We have to be able to move around. It's an iterative process. If you are staying here, you are going to fail. If you are going to stay here, you are going to fail. So we always go to the field, we learn, we come back, polish our model, go back, polish our model. So this is the way we should be looking at these problems. And then I also, this slide is a little bit of, I would have made this better, but this slide is actually, this is a groundwater hydrology as I knew it when I was a student many years ago. We were sitting here, and then all these things, we know all these things are important. I got my PhD, most of people got their PhD just working on these problems. Now, all my students, when they are doing PhD, they have to take classes, all these classes. You know, that the field has changed. So I think more and more we know the connections, we have to iterate between these things. But the important point I want to make is that I think most of the interesting problems are the interfaces in the disciplines. I think these are the places we are going to make a difference. So if you stay in your box, either this block grows, and this is reflected in some of the young people who are publishing papers in our journal now. This is the type of papers we see. These are the papers I see is going to make the impact, not what we do here. So I think this is an important thing I think we should remember, and my experience as well as others. Okay, so now I want to bring to my kidney problem. Actually, the reason I'm doing this is that I'm going to take a team to Sri Lanka, hopefully get some funding. We have got some funding. So the same irrigation system I talked about earlier. So this system, where this sophisticated system between almost 2,500 years ago, 2,800 years ago, the conditions were quite different. We didn't use fertilizer. We didn't use herbicides. We didn't know any of that. So they had this diversion scheme, brought the water from this place, we get 200 inches of rainfall, diverted the water, fed this irrigation system. Now we have a problem. We don't know exactly what this is the problem. That's what we are trying to do. We are going to go with the team. Again, I'm trying to twist some arms here, Scott maybe, and Will is going to go with me again. We have 23,000 deaths so far. 53,000 people, 450,000 at risk. This is a very small piece of the tip of the iceberg. These are males working in the fields, dispersing fertilizer, spraying pesticide, drinking water from shallow wells. So nobody, all the research, all the WHO did a study, all the study they are doing, they are all done by medical doctors. They are doing by toxicologists. So we are going to bring the hydraulic dimensions. I'm going to make an argument here. Actually, I'm going to give a talk. We are organizing a session on health and hydrology tomorrow, and I'm going to give a talk on this particular problem if you are interested. So you see, this is one of the ancient dams which are fed by this water coming from the wet zone. And then there are all hardness issues, water, other issues. So you see that there are no chronic kidney disease close to the reservoir. As you go down the canal system, they are the highest. So I have a conceptual model I'll present tomorrow, which basically say why this is happening, why you should be looking at. So we believe that this has to do with this problem. So the lesson here is that actually, so we were using this system, and we really didn't understand the social, economic, political situation here. Sri Lanka is the country which is the most fertilizer in the world. Okay, easy fertilizer, just put it in, but didn't understand. So now people are looking at this problem to see what's happening. Okay, those also bringing to thank few people, and it's a long road for me. Actually, this picture is from my sort of backyard of where I was born in my town, in the mountains. I said a lot of rainfall, a lot of green. This school I went to a Catholic boarding school. These are my physics and math teachers. I want to show this picture, my university. Siva is here. Siva and I went to the same university. Siva and I went to both these places. I went to AIT after that. This is my advisor. He's also a well-known hydrologist. He got his PhD at Colorado State. He became a very famous Thai engineer, and he became almost the Prime Minister of Thailand. So then this is my advisor, Ibn Morel Setu, who taught me many things and always said that don't be too sure. And if you work with him, he will tell you that. And then Professor Jovic, some of you know him. Actually, he's the person who gave me an assistance in Colorado. This is Art Corey. Actually, I met him last week. He's 94 years old, still going, still writing papers. He tried to give me a paper again on new diffusion theory. So it's very interesting to know him. And then these are my students, and all these red are you probably recognize some of them, and some of them are here, I think, and these are some many postdocs I had. And I was fortunate to have people from many countries in the world, all around. So I keep threatening my students that if I become homeless, I'll come and stay 1 day, week with each of them. So then I will have a place to stay. And then these are some of the people. I list a lot of names, and there are a lot of people here who are I want to thank, and these are the people who are my friends and who influence, and some of them are here. And then again, this is actually our new president of Colorado School of Mines. He's a porous media person. And then these are some of my colleagues, and then I spent my sabbatical. And then I want to actually use this picture. This is an interesting picture. We can see this. There are some, I actually started doing this experiment work when I went to a Gordon Research Conference, and then I met very interesting people. You see this, I did Dr. Witherspoon and Shlomo. This year, no, Shlomo is here. All of them have actually dark hair. Actually, I'm somewhere here. And then this is actually John Phillips. And then you recognize, some of them are sure here, but you won't recognize them because they all had dark hair now, including me. Okay, so I'm not going to read this. Actually, this is actually John Phillips wrote a paper in 75 years, and he said something interesting that you can read through this. The most important thing is, I believe, is that I think we are in the business of looking for truth. I think you can use your models, you can use your experiment, go to the field, observe things, and look for the truth. And this is really good advice, I think, to give to hydrologists. Actually, one of the problems we have is that there was a time that we had to compete with the IT industry to get our good students, but I think we have passed that stage. I think this is the most important thing for young people here. And the last slide I want to present, I want to thank my family. Actually, without them, I won't be able to do this. This is my wife. She's here. She herself is a good scientist in many ways, but you won't know her when you talk to her. These are my daughters. I tried to actually get them to become engineers, but none of them did. And this is my one who is in the back, and she's stuck with the two parents with two Apple machines here. And then actually they all end up with, none of them became engineers. They all end up doing a lot of human impact work, working with health, other issues, public health. And this is my only hope, and she was showing a picture to her on plows, and she really hated the plows. But now you show us lever, she really likes it. So she's my hope for an engineer in the family. And then I want to wish you happy holidays, and thank you for listening. And I have a tendency to talk very fast, and I was looking at Effie, and she was okay with me. Thank you very much, and I'll be happy to answer questions.
Don't leave. So I can ask the first question.
Yeah, good.
Now, Tissa, you presented a very broad portfolio of activities. The experimental work is not easy. I know, being part of the St. Anthony Falls laboratory. So I was ready to ask, before I saw the much broader problems that you have presented, if you were to tell me one of the most difficult things and challenges in really trying to mimic the real world in the laboratory. I have some experience with earth surface processes, but not in the subsurface. So there's a lot of work, but if you were to name one of the challenges, as we increase the number of processes we try to simultaneously model, what would that be?
Yeah, so I mean, maybe the answer can be long or short. So one of the problems with a field, again, is when you run the experiment in the lab, I sort of mentioned this, we really don't try to duplicate the field, because we cannot duplicate the field. So what we do is we try to identify what are the most critical processes in the field we believe is true. So if we look at these processes, we try to mimic those processes in the lab. So in the subsurface, obviously, is the heterogeneity. It's a spatial variability things. I think we can never duplicate the field in the lab. With the atmosphere, I think in my belief, this is subject to discussion, because the question is that when you look at the interface, when you look at the interaction of these processes, I'm seeing a lot of the coupling important at the scale, but all of you are working the larger scale know that this may not be important. But the fundamental, the question is that still the physics happen at the smaller scale. So how do you deal with the larger scale? So I don't have an answer, but the answer seems to be, how do you bring the most important processors from the lab to the field?
It's still a challenge. Please, questions?
This is the chance my students will have to. I should have taken 10 more minutes, yeah.
Yeah.
Mark, yeah.
So very nice talk, Tisa. I'd be interested in your wind tunnel. Do you have the possibility also for the movement of particles?
Yes.
In the,
yeah,
so
so
that would be interesting with your hills and
yeah.
the effect of the trees.
Yeah, so we use actually, so the technique we use the LDVs, where we introduce particles to measure the velocity. So we are writing some proposal called PIV system, which allows you to get the cross-sectional profiles. So in theory, we can put particle. People are very interested in looking at particle movement applied to many applications in agriculture. So there are a lot of possibilities of doing that. But again, I think when we designed the wind tunnel, we were not designing the wind tunnel to study the atmosphere, because that's too much for us to deal with. So we were actually trying to provide the best boundary conditions for the subsurface. We can control the boundary conditions. And in the process of doing that, what we are finding in this scale, at least the feedbacks are there. The feedback is there, but the question is, we never thought about the particle migration, but the particle migration itself is a wind problem. So, but in theory, we can do that. I think we are more interested in how these systems interact with each other. So that was the goal.
Hi, Tisa. Thank you so much for a great talk, inspiring. But I think one of the inspirations that you've provided maybe needs one more level of refinement on your part, and that is that you don't mean to just say that we spread more broadly in groundwater. There's some strategy in terms of, as Red's woman said, you got to know something about something. Yeah. And so, you brought to the table a deep knowledge of some key issues. And then can you talk to us a little bit more about the strategy of spreading out, the strategy of building those bridges, and how you do that strategically, bringing some depth, and then building the bridges across? So maybe a little bit more refinement.
Yeah, I think, so, as editors of WRR, we sort of tried to do that. We were trying to get people to send papers, but the challenge we have, part of the strategy should be how our university systems work. When people go for 10-year promotion these days, it is to their advantage to stay in the center of the center, because they can publish their papers and then they get their citations. As you move away from that, then you have trouble. The strategy, in my view, should be that funding agencies when I was at NSF, we were pushing hard the need for social sciences to work with us. The strategies are there, but I think the fundamental problem in my view is that even the journals cannot do very much these days, because when you really get out of the field, then we are getting into other journals. So I don't know. Maybe we can have a beer or something, and I can come up with a better strategy. One strategy is, I think, more people who are doing research should be really looking at the real world problems. Then you will spend some time working on your own area, get your papers out, and you have the luxury of really solving problems. Then you will be forced to move, like I did, into other areas. It never occurred to me to move to health. Unless one of my daughters, who is a public health person, told me that she goes to a public health conference, there are not a single hydrologist there. So I think that it is a much larger problem than we can help. But said that, I don't want to get it wrong. You have to be very comfortable with your core area. Then you explore these interfaces.
Other questions? Please. Probably you can say your name.
Audrey Sawyer. I was interested in your observations of how wind interacting with microtopography may redistribute soil moisture in certain cases. Is this does this only play a major role in certain places, maybe where there isn't much of an effect of vegetation using soil moisture? Can you comment on whether this might be important everywhere or just at certain times in certain places?
Yeah, so I want to clarify something here. So when you say vegetation, vegetation means a lot, you know. So what I was showing here was that we are interested in looking at alpine vegetation type of thing for the carbon cycling. We are looking at more grassy areas. So we are actually trying to do some experiments now where we will bring soil monoliths with vegetation. So the point I was trying to make is that the traditionally with unsaturated flow, people always look at unsaturated using Richard's equation, mostly a one-dimensional equation. So some of the phenomena we see in the lab under control condition, we have a poster which shows quite clearly that we are actually simulating a plant by using a very porous rock, and we see when the wind flows, the evaporation is like a wicking effect. And then what happens is then it started pushing water away from other places toward the tree. And one thing we are finding in some of the preliminary data is that the tree itself affect the boundary layer, and the boundary layer somehow controls the evaporation. So in the way, the tree is actually messing around with the boundary layer so that things make good for the tree. So my argument I'm making here is not applicable to big trees or anything like that. I'm looking at the vegetation distribution, bare soil, some places you have soil. So the second dimension come under those conditions. Said that, I would probably say that it matter of scale, and some scales, if you look at phreatophytes in the trees sucking water from the ground, there are quite a bit of lateral flow in the unsaturated zone. We don't really model in our traditional modeling. So, thank you, it's a good question.
Other questions? Yes.
Yusong Li. Tisa, so from your PhD work, you were a modeler. Then you changed to experimentalist. And then in terms of your research, it's been like changing different topics. You've been doing really well in each field. I just want to know what are the motivations that, what are the moments give you the motivation to change? And what are the challenges that you have met during those change?
That's a hard question. I think personally, my motivation was that I actually, like I said, I was not joking when I said that I grew in a place, it's a very nice place for hydrologists because we learn a lot of things by observing. So I think one of the things I decided not to do modeling was an interesting story itself. I wrote my first paper to WRR, early papers to WRR in the experiments, and that paper was rejected mainly because they said that my model is wrong. That's why I was not able to capture the experiment. And one review said the experiment is wrong. So I actually spent quite a bit of time trying to understand. So when I was actually interviewed for the WRR editorship, I basically gave this example that I think most important thing which changed my mind was that I see things in the lab. And then when I look at it, and I use all sorts of tricks, because like I said, I feel quite comfortable with modeling, but I was not able to match models with data. And I tell this story to many. We stop running heterogeneous experiments. We run homogeneous experiments in the lab. The reason when you run homogeneous experiments is people always say, oh, heterogeneity, you don't know where things are, so we can adjust things, get to match. Homogeneous experiment, there's nothing to adjust. You know the hydraulic conductivity? So they don't match. I had a PhD student who actually spent 2 years running an experiment, another 2 years, he couldn't match a homogeneous experiment. The point I'm trying to make with this long answer is that I think the way I change, the way I do things is that I sort of get away from, coming from Sri Lanka, we were taught very well mathematics and modeling, and I think looking at this experiment, looking at the phenomena, I suddenly realized that I think you should start your observation more than your model. So when you start something not happening, then you start questioning your model. It cannot be done for all the models because some of the good modelers here, you can never check your model. But the type of stuff I do, I can check my model because I believe the experiment is correct.
Great. Any other questions? Last one? If not, may I ask, is Laura Stevens here? During lunch, we'll present the Horton Research Grants, but I just wanted to see if some of you will not be able to attend the lunch to acknowledge 3 Horton Research Grant winners: Laura Stevens from MIT, subglacial hydrology; Emily Wojtek from Colorado School of Mines, mapping shallow groundwater flow patterns; and Adam Zvolowski from University of Colorado Boulder on moving beyond a snapshot towards a time-continuous understanding of hyporheic exchange. So congratulations to them. We will award them at the luncheon. So if there are no further questions, I expect to see some of you, many of you, if you didn't get a ticket for the luncheon, do not be shy to show up in case there are any cancellations. We sold 400 tickets. 150 tickets to students. Probably they were too eager to get one because it was free lunch. Some of them might not show up, so if you have friends that will be honored or whatever, just show there, because we have paid for 400 luncheons. And with that, it is on Marriott Hotel Marquis, Salon 7. And with that, I'd like to ask you to join me again in congratulating all our awardees, Tisa, Dara, and Tom.
Thank you very much for coming.